Okay, hello everyone. Welcome to the Great Lakes Seminar Series, co-hosted by the Cooperative Institute for Great Lakes Research, SIGLR, and the NOAA Great Lakes Environmental Research Laboratory. My name is Greg Dick, and I'm the director of SIGLR. It's my sincere pleasure to introduce today's speaker, Dr. Branko Kerkez. Branko is the Arthur F. Thurnow Associate Professor of Civil and Environmental Engineering at the University of Michigan. For those of you that are joining us from outside of UM, that is the highest honor for our teachers at U of M. His research interests include water, data, and sensors. His group is working to enable smart water systems, which autonomously adapt themselves to changing conditions using real-time data and controls. His research projects have spanned wireless sensing of large mountain basins, real-time flood forecasting, robotics, and real-time control algorithms for water systems. He's the founder of OpenStorm.org, an open source consortium dedicated to freely sharing hardware, software, and case studies on smart water systems. Before I turn it over to our speaker, I'd like to remind everyone to please leave your microphones muted for the duration of the webinar. You are welcome to enter questions into the chat box at any time during the presentation, and we'll moderate that at the end of the presentation. So with that, I'll turn it over to Dr. Branko Kerkez. Welcome, Branko.
Awesome, thank you. Thanks so much, Greg. Thanks everybody for inviting me. I think we'll just get straight to it. So I put this this image up here of most of you might recognize it as a Bob Ross painting, mainly just out of curiosity because I think a lot of people have been probably like practicing their pandemic hobbies, and so this one's for you painters out there. So anyway, speaking of pandemic, I wanted to introduce you really quickly to my two pandemic roommates over here. One of them is a big kid, at least this is what I'm supposed to say, and the other one's a pandemic baby. I know that's really original, but anyway, for these two spend a lot of time at home. In fact, in the last like 7 weeks, I'm pretty sure we only had like 4 days without one kid at home. But anyway, they share a common play area, which is where they do all their activities and all these other things. And most of you, I think, who have kids probably know that play areas don't look anything like this. They look probably something like this. And I throw this out there because in our household, we kind of have this important act. We have this, I think we call it a Clean Room Act. It's this kind of joint agreement, if you will, that we will reduce the clutter that we have because we want to reach some sort of outcomes. And so the way we do that, both my wife and I are engineers, is we roll up our sleeves and say, let's do it. This is the Clean Room Act. You're expected to clean your room, so start doing it. And so I bring this up because I do this with a twist at home. The thing I say at home is, we're going to go ahead and clean this room, but what I'm going to do is I'm going to turn off the lights just to make it a little bit more interesting. And you might think like that's really weird, like who would turn off the lights? How can you clean a room when the lights are off? Well, the good news I have for you is just like Bob Ross drew those paintings, Bob Ross is known for a quote that he's been saying, that he said for a long time, which is basically to say there are no mistakes. It's okay. Clean the room in the dark because basically you can't make any mistakes. Just go and do your best, and if you can just move stuff around, doing something is better than doing nothing. And so I just kind of want you to keep in mind as I kind of give you this challenge for a second, and I know it might be kind of weird kind of sitting at home looking at the screen, but I'm going to show you this messy room over here, and I'll just ask you to do the following. Stare at it for a second, because what I'm about to do is I'm going to turn off these lights, and you can think about how you're going to clean this room. So there we go, dirty room, here we go. Clean Room Act is in effect. Please go ahead and clean this room. So just imagine how you would do it. It's an intentional pause over here. So I presume some people are like, well, I would drop down on the floor, maybe I'd like shuffle some things around, probably push it under the bed if you're the kind of cleaner that I am, move some stuff in the boxes. And the question I would ask you after that is, how do you know that worked? How do you know that the Clean Room Act actually worked? This idea of like going to work and just doing a bunch of things with the idea of cleaning the room, how does that actually work? And so I know that's kind of a silly example, but I'm bringing it up to sort of just discuss, how do we actually know more important things, bigger things? How do we actually know that the Clean Water Act worked? Right? Just like we don't know if we're cleaning a room in the dark, how do we know that something like the Clean Water Act worked? And I know it's kind of like a big question, what does that even mean for the Clean Water Act to work? But the reality is, if your answer is something like, well, the Clean Water Act worked because, our rivers are not on fire anymore, then we got a problem. Because that's oftentimes the only thing we can point at. We can say, well, they're not on fire anymore, everything should be okay now, right? Needless to say, we still look around, whether it's across the Great Lakes or anywhere else across the country, really, and we still see algal blooms. We see them at massive scales, and we not only see environmental deterioration, but we see a lot of things that are impacting people's lives day to day, whether it's flooding in the back of your neighborhood or just really the kind of big flooding that we've seen across the city in Detroit most recently in 2020. So the point of a lot of this is just like wanting to take a dirty room and turn it into something clean. We can kind of look at, whatever your area is, whether you're a scientist, engineer, policymaker. When we have something like algal blooms on Lake Erie, and we want something else, we want the beaches to be clean. We want it so that when you search on Google Images, you don't get pictures of dead fish, you actually get pictures of clean beaches. What are we going to do? Well, we do something about it. Just like rolling up our sleeves and cleaning a room, we're going to roll up our sleeves and we're going to go and clean these watersheds, and we're going to clean the lakes and get this all sorted out. Now, big problems demand big solutions. I kind of wanted to show you, I'm in the civil engineering department, and when we think about big problems, we really try to bring in big solutions. So this is an image. This is the kind of thing that made me want to become an engineer. It's the Chicago Deep Tunnel. It's a project that maybe, depending on who you talk to, could have cost anywhere between $5 to $20 billion. But it's basically a giant hole in the ground that's supposed to capture all this runoff before it makes it to the lakes. And that has the benefit of reducing flooding and has the benefit of hopefully improving water quality. Now, most cities, the last time I checked, do not have billions of dollars to spend on infrastructure. And what they're being told in many cases is, well, if you can't do it all at once and fix a big problem, maybe you can distribute the solutions. And I think a lot of you that maybe work in agriculture have seen similar stuff like this. The idea is to sort of like bring in nature-based solutions that are going to help us at a smaller scale fix some of these problems. So things like green infrastructure or the basins and ponds in your in the back of your apartment complex. Maybe it's actually things like filter strips. The point is these distributed solutions have risen to prominence as the way to sort of solve the problem, because if we do a bunch of them over time, they're going to add up to benefits. So for those who can't afford big stuff like that big infrastructure in Chicago, maybe we can do lots of these little things. And there's a lot of benefits that are discussed with these all the time in terms of their scalability and the improvements they're going to lead to in terms of watersheds. So with this in mind, how can that be a bad thing? Just like we clean a room, obviously cleaning watersheds and improving all these things should add up to give us a bunch of benefits. And I kind of wanted to explore this a little bit to see what happens when we deploy these solutions. So here's the state of Michigan right now. I will highlight, I know there's folks from different states here on the call, so I'll highlight just where the University of Michigan is roughly. And I wanted to show you that even in the city of Ann Arbor, which is a relatively affluent place, considering tax base and a bunch of other things, we still have issues. It's not like our infrastructure is big enough to handle everything. And this is a picture from downtown from one of the rain events. And so city of Ann Arbor, just like all other cities, rolls up its sleeves and does a bunch of stuff. And this is just a conceptual example, but basically if you looked across a city the size of Ann Arbor anywhere in the United States, whether it's even a small municipality or maybe a larger town, city, et cetera, you might see a lot of these distributed solutions. A lot of times they look aesthetic, but in many cases they're actually like functional stormwater assets whose purpose it is to meet some of these end goals that we've set out. And so basically, what I'll do is I'll give you a conceptual example of what could happen when you deploy these infrastructure assets, these distributed assets. So what we're looking at here is about 10 square miles of a watershed in Ann Arbor. Again, this is a conceptual example that we'll go through here. And what happens is when it rains, all this water sort of flows to the top right over here and goes into the Huron River. And the city, like most other municipalities around the United States, went in and installed a bunch of distributed assets. So for example, if there's a development, they might put in a stormwater pond, maybe sometimes you'll put in some sort of stuff like green infrastructure. And the idea here is that if these are all truly positive things that we're putting in, then like Bob Ross said, there's really no mistake. Because basically what we could do is we could just go in and start layering one after the other, because truly if all of them are good and do something positive, then maybe I can just put them here, put them there. And as Bob Ross would say, there are no mistakes, because put them everywhere and everything will be hopefully pretty good, right? It might not be perfect, but doing a good thing can't possibly lead to a bad thing in the end. And so that makes Bob Ross, all of us hopefully fairly happy, right? It's a truly positive thing trying to bring nature back and solve all these big problems that we have. So what we'll do again in this conceptual example is we'll kind of take a look at just two of these components. So let's take a look at two neighborhoods over here. I've highlighted them as neighborhood number 1 and 2. And what we're going to look at is basically what happens when you install these things before and after. So what I'll plot here, and this is one of the kind of few plots at the introduction I'll have, is we'll just have hydrographs over time. So the flow or water level over time. You could even think of it as maybe stream erosion or something. Pick your favorite parameter that you want to restore. And so maybe before we install these practices in neighborhood number 1, water goes up and down when it rains. Neighborhood number 2, the hydrograph peaks when it rains. And the whole point here is that maybe we don't like this. Maybe these water levels are too high and we want to attenuate that hydrograph. So in classic engineering thinking, we install one of these practices in here, like the stormwater pond, to try to improve what's happening. And improve in a lot of cases means peak shave. Push the water around and make the hydrograph peak smaller. So we do that in neighborhood number 1. Neighborhood number 2, everything looks pretty good, right? Because this is what we teach in undergrad classes. It's better when the hydrograph isn't so high. And the interesting thing that can happen here, though, is if you're not careful, before these sites had this kind of additive impact. So imagine neighborhood number 1 is flowing downstream to the river, neighborhood number 2 is flowing downstream to the river. And before they added up to give you this kind of hydrograph at the end, at the outlet. But now if you push these sites around and you're not actually careful about the timing of all of this, you might actually have these flows add up to give you worse outcomes. So before they didn't actually add up, one arrived after the other, but if we just put in these practices and claim that we're improving things at the local scale, there's actually no guarantee that we can achieve better outcomes at the global scale. So not only is better plus better, not necessarily better overall, but it could even be worse. And there's some really interesting studies out there that I'd be more than happy to share with people and talk to people about, where it shows that basically just deploying these large sort of distributed solutions may not provide you the outcomes you're looking for, and it may in some cases lead to worse outcomes. So basically, the lesson here is stormwater systems and watersheds are systems. They're not just sums of their parts. You have to be careful about how you put that together. So, I don't know if this would make Bob Ross sad, but it makes me kind of a sad Bob Ross, because it means that all this we're doing, whether it's cleaning rooms or cleaning watersheds, we have no actual guarantee that it's achieving the things we want it to achieve. So, does the Clean Water Act work? I'm not entirely sure, right? And the whole point here is if you're just going to keep doing things and hope that through goodwill and through action you're going to reach some sort of conclusions or outcomes, then maybe instead of just doing, you may actually want to measure the outcomes. And so instead of just, what we're doing right now basically, and this is kind of the analogy to draw, is in many ways across the United States, this is not just regional, in many ways I feel like we're fixing water systems by turning off the lights. We just don't know what's happening. We're not measuring actual outcomes, and we're just doing things hoping they're going to add up to the benefits that we want them to add up to. And I believe when I kind of look at Sigler and some of these other organizations like GLOSS, measurement underpins a lot of what they're saying, which is basically the idea it's good to do stuff, it's good to roll up our sleeves and try to fix our watersheds and our lakes, but you do need to measure things in order to know if the stuff that you're actually doing is accomplishing outcomes. So it seems kind of obvious, but just to show you kind of what's happening, I know we have a lakes audience here, but terrestrially speaking, are we actually measuring stuff? So our primary source of water measurements in the United States right now, and therefore in the state of Michigan by and large, is the United States Geological Survey. So for watershed applications, they have lots of these different stream gauges. Over the span of the last century, the USGS has deployed something like 8,000 plus gauges across the United States. It is a monumental accomplishment. It took nearly 100 years to do this, but the United States appears to be covered by stream gauges that should give us indication of if the things that we're doing are actually achieving what we want them to. The issue that you run into here is that 8,000 gauges divided by 3,000 counties, which is how many counties there are in the United States, leaves you with a picture like this. So here's the state of Michigan. And what you'll notice here is that while we have some gauges that are measuring these watershed behaviors and outcomes, there are many counties, and I can give you examples across the whole entire United States, where we have zero measurements, like absolutely no knowledge of what's happening on the ground, yet we continue to invest millions and many millions of dollars into fixing water problems. And so this idea of doing, science in the dark or doing water management in the dark does potentially carry over to the way we carry these things out at a larger scale. In case in point, Detroit over here, the flood that happened in 2014 was actually the largest flood on the record in the United States as measured by insurance claims. And this image that it shows you right here is basically flooding as captured by neighborhoods, by people who live in neighborhoods and by the newspapers. If it wasn't for some of these photos and if it wasn't for insurance claims, we'd never even know that flooding occurred there. And it was such a massive flood that year, and all of it happened outside of the sort of federal floodplains, which is where we take water measurements. And so again, this shows you that we have a lot of these problems, we're trying to fix them, but we don't even know how much they're happening or where they're happening because it remains unmeasured. And so what this brings to bear is, if this is probably one of our only solutions to get these measurements at scale, how can we get more of it? Because basically a lot of these gauges are being retired, frankly, at an alarming rate. And a lot of communities, when you talk to them, will say, well, they're too expensive. And why are they expensive? Well, it costs money to run these, but if you open up one of these boxes, what you'll see is basically a lot of expertise that has to go in here to measure water systems at the resolution and at the sort of fidelity that we need to measure them. In many ways, when I look at a USGS stream gauge or maybe some of these other things that are out there that are measuring water systems, they almost require a PhD or at least a master's degree to operate. So it's not surprising that we have few of them, because they require skillful individuals to deploy them, and it requires a decent amount of expertise to carry this kind of stuff out. And I could see how that might be a little maybe in some cases shocking to some people, because we go home and we're talking to our smart speakers. We go home and our kids are being, you know, having discussions with robots and stuff like that. So why is it that for some reason all this technology is permeating our homes, but it's not permeating some of these crucial decisions that relate to how we're managing water? And so in this age of smart toasters and other kind of things that are all over our homes, that are, you know, listening to us while we're talking and selling our data to companies for advertising, what role do these technologies play, and could they play a role in how we manage water? And so this is an image we put together a little while ago that basically said, well, you know, what could these technologies offer us in terms of water management? And here we'll focus specifically on stormwater. So you could imagine, kind of in this discussion that we have these days about smart cities and self-driving cars, you could imagine a city that's covered in all sorts of sensors that are measuring things like water levels, water flows, rainfall, water quality, and then all that information is being relayed in real time to help us figure out if we're reaching certain outcomes. Sort of a really dense deployment of sensors. And then you can also do something with that data in terms of responding in real time, and I'll show you what I mean by that in a second. To try to bring some of these ideas to fruition, we decided a long time ago to try to open source a lot of these technologies, and a large chunk of what we built were basically sort of open source, cost effective, kind of cheap, I don't know how else to call it, sensing devices. And basically what you have is almost like, imagine your cell phone that's stripped away from all the things that you don't need. So you take away the screen, you take away the buttons and all the other stuff that's not needed, and you just leave the microcontroller and the cell modem. And effectively what this allows you to do is basically hook into this board a bunch of different sensors: rainfall, water level, soil moisture, water quality, etc., and deploy these boxes across entire watersheds to try to get some insight about what's happening. So the goal number one behind this when we started OpenStorm, which is the project that I'm about to show you, was basically to sort of like help turn on the lights. Beyond measurement, we're also doing a lot of real-time control, but I'll actually show you that in a second. I'll wait to show you that. What this allows you to do basically is collect data in real time. As soon as you put out one of these boxes, and we put out lots of them, so instead of having one per county, you might have one per square mile, all that data streams back in real time and is available for all sorts of applications. And so there's a number of applications I can show you right now. So this is an example where we're deploying green infrastructure sensors in the city of Detroit in partnership with the Sierra Club. This is a sensor that effectively measures infiltration of various kind of stormwater practices. So we just put them out there. It actually installs very quickly. Within an hour, all that data streams back. And this shows you the latest deployment that we carried out over the summer in the city of Detroit, where each one of those icons is a green infrastructure sensor that's measuring performance of these assets in the city of Detroit. I think we put out something like 25 devices in partnership with Sierra Club, compared to, I think, very few or none that were there before, which is not untypical in the United States. It's very uncommon to measure stormwater across these kinds of resolutions. But once you have it, you can pipe the data through all sorts of cool algorithms and other things that I'll talk about soon, to basically try to figure out what's going on in that system. And so when it rains, this just shows the water levels in each site after it rains. You get to see this sort of like dramatic level of variability in the system. Every single site behaves differently based on where it is, based on how it's constructed. And so they all of a sudden start taking this kind of like personality, if you will, that's not always represented by design manuals. And we can take these kind of data and put them into new kinds of maps that I think, frankly, some of the first that I've seen of this kind. This is what you get when you take all this real-time sensor data and create an infiltration map for the whole entire city of Detroit. This map follows, this is like very early map. I'm actually showing you something that came out this week, so we're still kind of validating the data. But imagine this is the map that you could look at to say, what does infiltration look like in the city of Detroit? So I could decide where to place these green infrastructure assets, bioswales, et cetera, to achieve some sort of outcome I'm looking for. So you don't run into situations like we saw earlier with Bob Ross, where you just kind of put it willy-nilly, or you basically say like, oh, let's put it in good soils and hope it works. This map doesn't follow, to our knowledge, soil types. It doesn't follow any of these other physiographic parameters that we've looked at. For those of you who want to know what it follows, it's very early results, and I'd be happy to take it offline with you. But it's basically an empirical map of GI infiltration in Detroit, and it looks nothing like we would have expected from physical equations. And so it just shows us that the data that's out there can actually be quite useful in terms of getting an insight into how these system functions, not just at a local scale, but really kind of at a global scale. And so we take these technologies and we scale them out further. So this is an example of our water level sensors. So these are devices that basically measure how far the water level is based on where you deploy them. So what we do is we put them out there. This is an example of Oakland County, which is Oakland and Macomb County, so Clinton River watershed north of Detroit. we worked with Eagle and a number of other groups to basically put out a very large sensor network. So we put out like 50 devices in the span of one summer on culverts, on bridges, even in parking lots where you might not ever see flow until it floods. The point is, by having a cost-effective technology, you can get these things everywhere. And then when you take a look at the watershed, you end up having a picture like this. So this is, I grabbed this morning to show you the latest image of all of our devices in Southeast Michigan. So our group, which is basically a group of graduate students and undergraduates, has deployed all of these devices that you see on here across the state. And we now even have a project with the Michigan Department of Transportation to start putting more sensors on bridges. So basically what we do is we go into watersheds and multiply the number of gauges by a factor of 10. So if you had one USGS gauge in your county, we usually put these in and you end up with 10. And this allows you to give this kind of granularity that leads to images like this. So this is the Clinton River watershed north of Detroit, 800 square miles roughly, and this shows you water levels after a storm across the whole entire watershed. And so it gives you a level of granularity that really was not apparent before, and it shows you the tremendous amount of variability that may have been difficult to capture through any other means. And so as soon as that data is available, we can start using it for all sorts of applications. So at the local level, we're working with counties and fire departments and others to do simple things like, if a sensor is on a bridge and the water levels get too high, you might want to send out crews to close off that bridge or send out notifications to residents. The data are being used by a variety of groups for things like watershed management. So there's lots of reservoirs on our watersheds. There's a lot of managed lakes and other kind of things. And so this informs not just how those assets could be managed at the larger scale, but also we do a lot of monitoring with counties and municipalities to see if the local requirements they have for stormwater construction are actually working as desired and if they're reaching their desired outcomes. And so this is an example in Washtenaw County where we're working with folks to basically measure their GI practices that they're trying to understand right now. So there's a lot of kind of palpable, seemingly useful applications of just having data that wasn't available before. Which brings me to the next step here of, it's good and interesting to collect data, but what if you could do something about it? And by do something about it, I'm specifically showing some images of self-driving cars here, mainly because that's where I am. I was just talking to Greg earlier about North Campus. North Campus at the University of Michigan is where you see a lot of these self-driving cars. And the question is, could you bring to bear some of these technologies to water management? So if we go back to that image that I drew earlier in terms of, we have something, we want something, it's not just enough to do something. Is it enough to just measure something? Can you do more? And the idea here is you could do more. If you determine that something's not working the way you want it to work, like as it was constructed, or maybe you just don't like the outcomes, you could conceivably adapt, and you don't have to wait to adapt in the long term over the span of 50 to 100 years, which is how often our infrastructure gets replaced, but maybe you can do it in real time. And the way you can adapt in real time is by actually controlling the flow of that water. And we do this using valves. So here's an example of one of our internet connected valves. You basically connect it to one of the sensor boxes I showed you earlier. And with this device, you can actually control the flow of water. So imagine, again, a self-driving car steers itself in response to changing conditions. A self-driving valve, if you will, could maybe move water around to achieve some desired outcomes. And so here's an example of one of our early sites that we deployed in partnership with Washtenaw County here in Ann Arbor. What we basically do is we attach these valves to existing infrastructure. So there's no building new infrastructure. You just go to a site, for example, like the one in the left bottom corner. It has an outlet. Before, the water would just go in, water would go out, and that's basically what you get. By adding the valve, you can decide when to let water out. So for example, you could hold water after a storm to let the sediments trickle out, and then check the weather forecast. And if it looks like it's about to rain, you slowly open it and release the water to create more room for the incoming storm. And some of the sort of water quality benefits that we saw very early here, like in this site over here, when the valve is open versus the valve is closed, by retaining water longer, you can start seeing some significant benefits of just repurposing that infrastructure. So stuff like 6 times the amount of nutrients captured, twice the amount of sediment capture, and that should make a lot of sense, right? Because instead of letting the water flow out, you're holding it in place. But traditionally, we don't design a lot of infrastructure like that because when a flood comes, you need more storage room. And so the valve allows you to basically have both. Where this becomes interesting, and this is actually where the bulk of our research is what happens when you have multiple valves? So for example, we can imagine, again, let's just conceptually say this is the city of Ann Arbor. I have 2 neighborhoods. When it rains, the water flows downstream. And if it rains too much, you might get flooding. So that's that green line that I show over here. So a kind of classic hydrograph. if you add valves to the system, you could take advantage of underused capacity. And so by that I mean is something like, let's say neighborhood number 1, it's raining a lot, and neighborhood number 2, it's not raining a lot, and you have some unused capacity there. Maybe you close that valve, open the other valve, and kind of like squeeze more performance out of the system in real time. So really coordination across the scale of the whole entire watershed, not just individual sites. And so to show this concept at work, what I'll do is I'll focus on this watershed over here. And this is a classic example of something that we see over and over. You might have this watershed, water's flowing outside of it, and we have a sensor downstream that determines that there's flooding there. And so what we can do, for example, say, well, if that sensor is detecting flooding, maybe a valve upstream could be holding back water to make sure that that doesn't happen. And so we carried this experiment out in the city of Ann Arbor. What you see here is about a few square miles. On the bottom left is a 5 million gallon stormwater basin that was built in the 70s that we retrofitted over the span of a few days with the county. And what happens here usually when it rains is the water flows downstream. So all the wash off from all these neighboring roads and culverts and stuff goes through this basin and then goes into this downstream wetland that was constructed. And the purpose of this wetland is basically to take all that water, treat it, naturally treat it before it goes out of the watershed, and serve for flood protection. But what happens in most cases, like most infrastructure, is undersized, and so it'll flood a lot of cases or overtop when it doesn't have enough capacity. And so the experiment was really simple, going back to what I just said earlier. If you detect flooding downstream, so you place a sensor in that downstream wetland, and then you only send down water when there's actual capacity. So the valve will only open when downstream is ready to take those flows. And so this is kind of the video that we see of this right here. So this is after a storm. This is the upstream basin, and what we're doing is we're holding water right here. And when we know that it's possible to send water downstream, meaning it's not flooding downstream, we open up that valve. And so the plots I'm showing right here on the left-hand side is the water levels in the basin. When you open the valve, they decrease. That's not shocking. That's what happens when you open up a valve. And then the water arriving about an hour and a half later in that downstream wetland. And a closer look at that wetland kind of shows us this image over here. The water levels in this video are changing from the red to the green line. And because it's not raining, we know that the only thing that could be causing those water level changes is the upstream control from a site that's like, 1 to 2 miles away. And so this is kind of a really interesting kind of example that shows that you can control something far away at a very granular level. And to just put things into perspective, because you're not sending all that water down all at once, you're giving the site the ability to do what it was designed to do. It's supposed to treat nutrients, it's supposed to, combat flooding and do all these other things. And the county put together a bunch of metrics that show what happens with nutrient uptake and some of these other conditions. A big takeaway for me was just something that we keep seeing over and over again in this research, which is that if you add real-time control to infrastructure, you effectively make it look twice as big as it actually is. So in other words, if I had to build that downstream site to take all those flows, I would have had to make it twice as large if I didn't use real-time control. And so that would mean building into parks, building into nearby homes, and oftentimes it's infeasible. And as I learned from Evan Pratt, who's the Water Resource Commissioner here, in his words, you're boxed out of development. In a lot of cases, even though you want to build stuff to reduce flooding and improve water quality, there's few places to put it. And so again, going back to his words, adding real-time control allows you to squeeze more performance out of existing infrastructure before you consider putting a shovel in the ground to build more stuff. And so they did a bunch of calculations on this that basically showed that if you had to make that site bigger, it would have cost $1 million to achieve that. Whereas the valve, again, I'm not counting student time, but a valve costs a couple $1,000s to put in, and off you go. And the cool thing is you can change what it does every given time. So in this example over here, we're sending water down, but I came down and I looked at what the students were doing one day. I was visiting lab, and this is our watershed in Ann Arbor. And for all of you who want to see this in person, you can ping me, and we usually do tours of this. Lots of sensors, a lot of valves. And I showed up, and the students were plotting the real-time water levels downstream of the watershed. So all the water flows kind of at the top right in that watershed. And they were controlling the valves in the watershed to actually spell the Michigan M in the hydrograph. So this is 2 valves coordinating between each other to create this hydrograph shape, which seems a little bit silly to be drawing letters in a hydrograph, but to me, this just shows the level of fidelity that you can accomplish. Because basically, if you can spell letters in a hydrograph, you can very precisely achieve other outcomes that you have in mind, whether it's flooding, whether it's nutrients, whether it's erosion, etc. So it really brings to bear this notion of self-controlling watersheds, autonomous watersheds that may or may not become, a solution down the road. But for now, they're showing that, before we used to put stuff in and hope that it works. Now, if it doesn't work, you just change what you're doing, and you can change your strategy the next day if you want to. And so the question that brings up is basically, does this scale? Does this only work in a 10 square mile watershed? And the good news is that we've been collaborating with Great Lakes Water Authority, which is our regional water authority here, to see if some of these techniques can actually work at the scale of entire sewer collection systems. And so the students did a project some number of years ago, and there's been a lot of updates since, looking at the entire collection system. They already had hundreds of sensors that were collecting data. They already had control points, pumps, gates, valves. In fact, the control points they had were really cool. Like, imagine a 30-foot sewer pipe, and when you press a button, which is what the operators can do, it starts inflating this big pillow. And that pillow effectively serves like a dam that can hold back water. And so this pipe that would typically only convey water now can serve as a storage asset. And so we spent some time ago, a number of years ago, looking at this and trying to basically say, sensor data are cool, machine learning is interesting, but how do we actually make this useful to people? So we've been spending a lot of time building dashboards for operators to basically take all these hundreds of sensor streams and actually turn them into sort of actionable insights. And the models that came out, this was like almost 2 or 3 years ago, basically showed that just by controlling of the portion of the system, you may be able to reduce combined sewer overflows by 400 million gallons, which is quite significant. To put that in perspective, if you wanted to build a 400 million gallon storage basin, like Chicago did, a very large basin, it would cost you $500 million. And so, that's kind of an interesting thing, because basically says, it's like that phone number, call before you dig. Before you dig, there might be an opportunity to reprogram your water system, which is kind of a weird concept, but you can reprogram what you're doing, change what you're doing in real time, squeeze more performance out of it, and then decide where you want to build more storage assets. And this project is ongoing right now with the Great Lakes Water Authority, and a bunch of other groups are working on this right now. Actually, real consultants and companies have come in to kind of look at implementing this stuff regionally. So with that in mind, when people see these kind of examples, oftentimes they ask us, okay, if I want to build a smart water system, and if I want to build a self-driving watershed, what is the actual recipe to this? And the recipe is kind of straightforward. You need technology, which is what I've basically been showing you. I've been skipping over probably the larger portion of it. Was technology and raw data are one thing, but you actually need to turn this data into actionable information and insights. And for that, you need a lot of math. And so this is my obligatory math slide to show you here that when it comes to controlling water systems, when it comes to taking noisy sensor data and turning it into something useful to build real-time operational systems, you need a lot of math. And I'll skip over the math that we use for our watersheds, and I'll actually focus on some math that I was kind of thinking about in terms of lakes over here. But effectively, what our lab does before we go on to the next section that I'll briefly cover after this is we take knowledge that we've had about water systems for quite a long time and try to embed it in these mathematical algorithms. Some people call it machine learning, artificial intelligence, all the same stuff. It's just a bunch of fluffy terms that basically mean applying math to real-time data to get it to do something. And so when I was talking to Greg before I gave the seminar, he said, you're doing a lot of stuff, and kind of, I think of it terrestrially, like in watersheds. What implication does this have for the Great Lakes? And so I kind of wanted just to close this off by showing, like, if you wanted to have a recipe for smart lakes, what does that look like? Well, the good news is that a lot of people have already thought about that. So there's a Smart Great Lakes initiative that's already ongoing, and there's a great report on it. And I spent some time reading it in preparation for this discussion over here, but it gave me a bunch of ideas about what other people already think might be the recipe. And I kind of picked 2 quick applications to show you of how this could be deployed on lake systems. So one example here is, as probably all of you already know, Gloss already maintains an incredibly impressive system of buoys across the Great Lakes. But it's not unsurprising that, if you talk to anybody who looks at either buoys or stream gauges, there's never enough, right? You always kind of want to add more because some places are not covered. So basically, again, this example I gave about the USGS and the lack of gauges, we always need more data because we want the ability to basically measure outcomes. And so with this in mind, if you don't have enough data, where can you find data sources? So just like I showed earlier, you can build your own sensors, or in this case, we actually had a project where we saw that data were already being collected. And they were being collected by volunteer ships, and this is called the Volunteer Ship Observing Program. It basically means that a lot of vessels that are traversing the Great Lakes, a lot of them for commercial purposes, have weather data on them, have sensors on them already for navigational purposes, but this is shared conveniently in a bunch of text files on some server, so not exactly easy to access. it is measured in places where the buoy network doesn't cover it. So on any given day, I'm just showing you, for example, this is some number of years ago where a ship was driving around the Great Lakes or floating or whatever ships do. You know, I'm not a not a naval person. Basically shows you that it doesn't necessarily look like that ships traversing the lakes give you a lot of information. But if you look at it rather than on just one day and you look across it as a season, you see that the number of observations that are made by these ships, and in some cases, somebody could look at this and say it's not quality scientific data, it's just ship data. Well, it's a lot of data. And when people talk about big data and other kind of things, you know, the student and that worked on this, Kevin, we jokingly refer to it as big ship data. Basically, what can you do with a lot of data that maybe somebody wouldn't necessarily look at for day-to-day use? And so what we basically did is we compared all these measurements that are made by these ships to some computational models that were running in real time at the time. So this is the NDFD forecast system. I bet a lot of you know it already, but what this is basically plotting is just what is an observation made by the ship and how does it compare to the model, the state-of-the-art model at the time that's predicting stuff in the Great Lakes. And so here we're just showing temperature of the water surface, for example. So what you'll see is models do a pretty good job, but there's these kind of regions or these biases on the left and the right-hand side, whether it comes to really cold temperatures or really hot temperatures, which are both kind of really interesting from a climate change perspective. Why are the ships observing something else? And so rather than building a brand new computational model, which is not our expertise, we kind of went to machine learning for this. We basically said, okay, you know, a boat is going around, a ship is going around, and what we're showing here is just, for example, wind speed. The wind speeds made by the ship differ from the model, not just in space, but they differ in time. So different seasons, the model is more accurate than others, or I shouldn't say more accurate, it agrees with the ship data more often, and different points in space agree with ship data. And so the idea is, if that's the case, could we somehow use the ship data to correct the models, if you will, fuse these two things together? Sometimes people actually use the term sensor fusion to achieve this. And so how does one take something really weird like floating ship data that's maybe not the highest quality data according to some, and turn it into a spatial estimate of stuff like wind speed or temperature? And so if we go to traditional approaches to do this, and traditional, I mean something like a typical regression model that most people wouldn't consider machine learning, but it actually is. And what I'll do here is I need to probably go quickly on here just because I see I'm running out of time here. I want to save time to talk to everybody. But typically to run something like a regression model on this, meaning the ship is going across some point in space. If we wanted to make a prediction at any given point, we'd have to fit some pretty nonlinear curves to this data to make this happen. So for example, let's say we're trying to fit wind speed, the ship is going along. It's one thing to just draw a prediction and try to fit curves to the data. It's another to add kind of an uncertainty bound to it. So some more sophisticated regression models will oftentimes use probabilistic estimates to accomplish this. But it turns out that typical kind of classic regression, like you carry out in Microsoft Excel, might not be up to the task. And this is where we kind of draw upon some other methodologies, which broadly fall under this. You know, if you drew a circle around machine learning methods, you would see this. This is known as a Gaussian process model. It's really cool. I teach it in class, so I mean, I think it's cool, but it's really kind of fascinating because it basically says, instead of trying to fit a line to the data, why don't we just assume that there's an infinite number of curves that fit the data? So imagine an infinite number of maps that give you all the possible wind speeds in the Great Lakes. And the point of our approach is to basically take those ship observations and take the model outputs that are created by NDFD and see which one of these models is more likely. So basically saying, yes, there's all these possible wind speeds and temperatures on the lakes, but once we have all this weird data and once we have all these model outputs, can we fuse them together into something that's the best possible model? And so there's a lot of cool tricks to do this, and it turns out, you know, the folks in computer science have been thinking about this a lot, and in statistics have been thinking about this a lot. There's a lot of math that allows us to do this in a very generalized way. In this particular case, we're using kernel-based methods that basically allow us to determine what the best possible model fit is. And so in the interest of time, I'll just tell you that once you crank open this box of machine learning methods, you have to be very careful because you can create something that's an amazing model. It fits your data perfectly, but it could be kind of completely wrong because it's overfitting the data. And so we actually spend most of our time when we're working with large data sets, cleaning the data up and working through a bunch of model selection approaches to make sure that we don't have a model that believes all the ship data, or we have a model that believes all these kind of physical model outputs, but we have some sort of parsimony in between. And we can use some sort of classical sort of statistical approaches to sort of say, you know, in this case, let's maximize the likelihood of that occurring. Let's maximize the likelihood that our data, you know, these observations that came from the ships actually match what could be going on in there. And so for anybody that wants to talk to me, offline about this, for this talk, I removed a lot of the math, but at the end of the day, we're a bunch of engineers. And the good news is that artificial intelligence is not artificial, it's not intelligent, it's just a bunch of math from the 50s, and we finally have big enough computers to run this stuff on. And what this allows you to do is basically bring together these different things that were not really compatible before. Most physical models, you can't just shove data in there and hope something that happen, something good will happen. In fact, you can't even shove data in them in most cases. But with this kind of approach, you can fuse state-of-the-art physical models with these observations to create brand new kinds of maps of these kind of parameters that I was talking about. So before, maybe, for example, temperature did not match the modeled result as closely. Now with this kind of approach, it matches it really, really closely. And at the end of the day, I'll just skip straight through it. It allows you to make new maps. So before we thought, dew point looked like this. Now with the ship data, it looks like this. So basically what it's saying is, until the day when we get lots more buoys and all these cool observational things that I know are in the works right now through the Smart Lakes initiative, there is also an opportunity to use sort of lower cost sensor data to try to create sort of better estimates of what might be happening out there. And I will just, just in closing right now, just like there's the way to use data to come to some sort of conclusions about what might be happening. Earlier, we said you can add valves to create self-driving water systems. Well, there's also room for autonomy on the lakes. And I'll just show you really quickly a project that we were working on that basically said, you can go out and manually sample all these things, which brings to bear, again, this idea of manually doing, USGS samples, and you only have so many of them, and maybe replace it with robots. And this is an example where we just had a really simple concept that basically said, could a robot adaptively sample hypoxia or algal blooms on the lakes? And that's kind of what we built. We built a prototype that was on smaller lakes. So here's a robot. It has a winch and a sensor attached to it. And the whole idea here is it's going to drive itself around the lake and very quickly try to figure out where to sample next based on prior conditions. And so we built a back end to it. We connected the cloud, all that good stuff that I was showing earlier with the valves. And what this thing basically did is it adaptively drove itself around based on this algorithm that we constructed with Laura Balzano, who's in electrical engineering. So she's like a data expert that basically would take a robot, try to delineate, let's say in this case, the hypoxic zone, areas of low oxygen on a lake, by finding the area very quickly and then traversing in an optimal way up and down to kind of stay locked onto that area. So instead of just sampling at even points around a grid, you're effectively just locking on and using this algorithm and crunching data in real time to try to determine where to take the next sample. And so we carried this out on a lake right here next to the university, and we showed through this experiment that a robot that moves around, and I only bring this up because I know there's a lot of work being done with unmanned craft on the Great Lakes, a robot that moves around in a constant trajectory or at an even grid, it takes it a really long time to delineate things. In this case, to delineate the hypoxic zone on this lake, it could have taken almost a full day to do it through an even grid. This robot did it in 2 hours by adaptively changing what it's doing. So just like the valve changes what it's doing, this robot changes what it's doing based on what it's measuring. And so that requires some back-end computation and all sorts of other stuff. So the idea here is if anybody's got some cool craft out there, which I know some people do, I'd love to just chat and see what you all are doing and how you are deploying these things at scale, right? Because our group is just kind of thinking about it algorithmically or abstractly. It'd be really interesting to see if this stuff has relevance out in the real world. So I will end the talk now on a Bob Ross painting again, just because why not? We started that way. And just ask a question and see what all of you think. We are talking potentially about smart lakes. We're talking about smart watersheds. And it's not just lakes here, I include the stuff that I talked about earlier, but does adding technology really provide us with all these benefits? Does it mean that if we start sprinkling sensors around in this lake and that lake and another lake and all these lakes and all the watersheds like I showed before, does that lead to actual benefits or is it true that there are no mistakes if we just add more data out there? And one could argue, how could that possibly be the case? But other people have used technology and have taken it places where maybe it led to weird outcomes. And I can give you tons of examples, but everything from Wi-Fi connected babies to juice machines that only work when they're connected Wi-Fi to egg cartons that are connected to the internet and tell you how many eggs you have. A lot of people could look at this and say this is silly. But what I would say is in the early days of smart water systems, getting enamored by technology and pretending like that technology and AI and all these things have a role to play in water, what is going to stop us from making things that are not actually useful for people? So just because something's really, really cool and kind of like there's some cool demos of it, how are we going to make sure as a community to make, to sort of make this technology something that's used appropriately and is actually useful to people on the ground. So I'll just end the talk by saying, see what you think, but smart is not necessarily always useful. Smart can be cool, all these different terms that accompany it can be kind of interesting, but it's only useful if we ground it in real applications that are actually useful to people on the ground, which is oftentimes not academics. Those are the actual people that experience water systems. And so the question is, who's going to tell us what we should be building that's actually useful? So that's it. I will end here, and I think we got a little bit of time to just chat.
Okay, thank you, Branko, for that very interesting and stimulating talk. That was great. I'm going to turn it over to Nicole, who's going to moderate the question and answer session.
Thanks, Greg. Yeah, Branko, that was really wonderful. Thank you very much for the storytelling. It really sort of puts it into perspective for you. So we'll start with our first question that we received a little bit ago. Have you considered using remote sensing data, of course, satellites, to fill in the data gaps?
In short, yes. So depends on the, I don't know the motivation of the question. There's a specific data set that folks have been thinking about, but there are a lot of large scale data sets that are provided on a regular basis by, let's say, the federal government. So terrestrially, there's things like soil moisture that's measured by satellites. There are obviously like remotely sensed products that give us not just hydrologic, but actually weather conditions and stuff like that. So there's some cool stuff out there. Some of the things I've really enjoyed is actually beyond the remotely sensed product. We even have a national water model. So there's a group sitting in Alabama right now that's running a national continental scale water model. And the outputs of that, one could say, are not, fine enough to help me do something on the ground. Or again, like with the ship data, we could say, well, actually, could there be some use in that? Could we combine it together and actually extract something on the ground? Now, I think there's people in this audience who probably know much more about remotely sensed data on the lakes, but the answer is that if you want to combine all those things, they don't shove into tools that we've built already. So you can't just take data and put it into models. That's not how they were built. But the good news is with a lot of the stuff that's out there right now in terms of these data methods, again, loosely using AI and machine learning, that's just a catch-all term for almost nothing. There is a way to put data tools together to bring those things together. So we've considered it, and I'd be happy to talk to whoever asked that question about specific examples of that.
Thanks for that. That question was asked by G Poo. I hope I'm pronouncing that correctly. We have one from our colleague Bopi Bindanda out at GVSU. Leveraging the computational power of smartphones to sense watershed variables and take remedial steps, i.e. real-time flood control, looks promising. Do you have any problems with vandalism in your field sites?
Yeah, that gets asked a lot, actually. People ask about vandalism, and a lot of people ask about like cybersecurity. Yeah, I mean, anytime you scale out a technology, you're going to, the more devices you have out there, the more likely it is for a teenager to find it at night and smack it with a baseball bat. And that has happened. But the good news is they're becoming smaller, they're less visible, and actually the maintenance associated with deploying these is much less than, like, let's say, keeping up a really large gauge that's like super sophisticated and stuff like that. So vandalism happens, but it's surprisingly not that big of a deal. It's much more common, let's say, to have a massive flood that'll come through and then like put your stuff underwater. So we've had some units taken. It's actually quite flattering when they steal it, because I'm like, I hope you get some good use out of it. I don't know what they're going to do with it, but it's honestly not it's not our biggest problem. Let's put it that way. Like, not even close.
I'm going to follow up with a question of my own then. Do you have any troubles, or how cumbersome is it do you have to go out and revalidate? Do you have to go out and clean them up? A lot of our equipment that we put in the lakes has to be cleaned up, once every couple of weeks or so. Do you have any of those issues to deal with?
Yeah, I mean, so like just maintenance, and specifically, I mean, the conditions of deploying in the Great Lakes, like I envy everybody who works on that, because it is a tremendous amount of expertise that goes into doing that. So you have biofouling, you have ice, you have all these different things. The bulk of our devices are non-contact, which basically makes it so that we can put them out there and hopefully leave them out for years. That said, stuff does happen. You just kind of have to deal with it. The cool thing is that you can use a lot of these back-end services. So that's something I didn't necessarily talk about as much, but a bulk of the tools that we build are not just for people on the ground, they're for us. It's to figure out when something needs to go out, when something needs to be swapped, if a sensor is drifting or if it's getting noisy, to kind of grab it. So it's something that we've dealt with here or there, but again, the choice of technology on the hardware coupled with the choice of technology on the data backend helps us kind of manage that. And again, looking at the map that I showed earlier, you know, it's multiple thousands of square miles, and it's all done by a team of undergrads downstairs who are incredibly capable. We have really good undergrads, but still, like, you know, it's not, we don't have dedicated staff for this. Like, it's literally all kind of volunteer work. I don't know how else to put it. So.
Thanks. Another question from Hayden Henderson. Is there an easily identifiable tipping point for when time, dollars, effort is better spent focusing on getting 5 precise observations versus interpolating 500 observations of varying unknown precision or reliability?
Sure. So basically, you know, if I can restate the question is, people ask it in different ways all the time, but like, should I pay for one really, really good gauge like the USGS, which is great, gold standard? Like, we look up to them. We have a poster in lab. Like, we're like, you know, we love the USGS. Should I pay for one of those, or should I pay for 10 cheaper sensors? To me, it's like, what are you looking for? Because basically, if you want to know if the parking lot in the Walmart is flooding, you're not going to know that using the gauge. You're just not going to get that. And so what we've observed is it depends on the application, right? And so I think there's some kind of parsimony there. It's like one really good measurement, sort of flanked by a bunch of different lower cost measurements to allow you to get at those kind of things that would be tricky to get otherwise. So depends on what you're doing. If you're a modeler and you really need that precision on the ground, then you need that USGS gauge. Otherwise, if you're somebody who just wants to know what's happening broadly and I need to confirm it so you don't rely on newspaper reports to tell you otherwise, then those other devices. So I think it depends on the application. But well, it's just, I guess, one comment on that. Again, just picking USGS because that's what we do. Is we do a lot of this. I call it terrestrial. I don't know what to call it, Greg. But like, a lot of their mission right now is to improve these stream gauges. And when I've been to a lot of meetings where there's discussion about we're making them better, they call them super gauges right now. So the gauges are getting more precise, but there's always people in that chat room and those webinars saying, but we can't even afford the regular one. How am I going to afford the super gauge? When am I ever going to get this measurement, you know, on this road crossing? And so I don't think it's a competition between the two. It's literally like one for one thing and one for another thing.
Sorry, I muted myself.
Okay.
Another question. Were the rain garden sensors in Detroit measuring surface water level or water level in the soil matrix?
Okay, that's a really, really good soil question. So I got to make sure that like that's not my expertise necessarily, but we paired up on this project. We teamed up. But basically, what I can say on this one is we drill into the ground. We're basically measuring water level, and then we're using a bunch of techniques that were published in other papers to try to sort of estimate the infiltration. Now, that said, we have sensors for soil moisture, and we actually have sensors for matrix potential. I wasn't showing that data, and that's possible data on there. So you can get the kind of soil water balance and the soil moisture content fairly accurately from those devices. But the ones in Detroit were almost like mini wells. That's what we did in that deployment.
Interesting. We have a couple of questions about how these devices communicate. One is are the open storm systems telemetered via traditional cellular modem or an IoT modem? I'm sorry, I don't know if that's.
Yeah.
That's fine. And then to follow with that, is there any issues with these devices failing to communicate remotely? How do they talk long distance, etc.?
Okay. We set out about when the pandemic started, we kind of rehuddled as a group and we're like, what do we want to do? And our goal is basically like, can we make a device that could be in the field for 5+ years? And that's actually motivated by the fact that communications technologies turnover at that rate, 3G to 4G, 4G to 5G, and all this other stuff that we're seeing right there. So it would be dictated by the duration of the actual existing network rather than the sensors themselves. That said, we do spend a lot of time on looking at sort of wireless reliability, and that's chosen strictly, again, based on the application. So we've done it all: satellite, long-range wireless, mesh. We've done cell. In fact, like most of our networks right now are cell. We're using cell phone modems. We have agreements with the carriers that make it so that we only pay $1 a month instead of having to pay like $70 per device and stuff like that. And that's what I hear a lot of times from people. It's like, I'm choosing a technology that gives me the longer, long-term lower cost. But the reality is a lot of the cell phone companies right now, and even satellite providers, are recognizing that they can't just charge crazy prices for stuff anymore. They have to offer some sort of other pricing. And so the nice thing about something like a cell network is it works everywhere. and doesn't just work in the US, but works everywhere. So we use, I know this is not a good answer to, but we use whatever works for us wherever we need it. So if we're in the UP, we're obviously going to use whatever works there, which might be satellite.
That makes sense. Thank you. We have a question about the stormwater units and how they measure. So it says your stormwater units seemed to primarily measure infiltration rates that may measure water levels in a swale after a rain. Do you prepare a swale or just stick it in and measure its personality? Are you simultaneously measuring rainfall and or evaporation? And how many devices in a system?
Whoever asked this, we should just hang out. I'll tell you everything about it, because that's in itself is probably a 30-minute discussion. But yes, we have access to 50 plus rain gauges from the Great Lakes Water Authority. There's a bunch of other measurements there. I think there were some groundwater wells in some cases that the students found. If we just go in and measure their personality, that's effectively what we're doing. So Sierra Club has been deploying these rain gardens in the city for quite some time. And so they chose the sites. So that was actually an example that was not necessarily driven just by our scientific curiosity about how this stuff functions, but it was actually partnering with somebody in the community and saying, what is it that you're interested in? So in that case, we actually put them in places that they chose for a variety of reasons. And they're interested in seeing if the designs they build for their rain gardens, if they, as constructed, if they perform it like they would have anticipated. So yes, we just stick them into stuff that already exists. With just an auger, you just put an auger in there and pop the unit in. There might be better ways, but it seems to work pretty okay.
Great, thanks. You tapped on this a little bit, but Bill Schultz is following up. Open measurements is one thing, open control is another. What about security?
I always like to say, what about it? Yeah, so it is true that when you connect things to the internet, you expose it to a new kind of risk. There's no doubt about that. What I've seen over the years and generally presenting on this topic, so it's not like we're kind of super new to it, but it took me a while to realize that existing approaches have a risk as well. So take a county in the United States that has absolutely zero measurements, let alone control. There's a risk of doing business as usual that's quite significant, which is to say, if you look at the news, you see things are flooding. So it's not as if existing solutions can wash their hands clean and say, we're perfect. In fact, did the Clean Water Act work? That's kind of why I'm like being silly when I ask that question. Now, that said, connecting stuff to the internet opens up new risks, which brings up a question of what do people want to accomplish? It's up to them, right? Like, are you willing to take on a little bit more risk in order to achieve these kind of outcomes that are possible with these technologies? What I have seen, without drawing in a broad brush, is that by and large, the consensus right now appears to be from utilities across the country. We'd rather be safe and not connect because of all these risks. But you're also leaving value on the table when you do that, because all these technologies are permeating our homes and we're seeing some of these benefits, like cars are driving themselves. Are we truly going to never connect our stuff to the internet? And the answer might be yes, and so be it. I'm not the one to promote one thing or another. What I'll just close with is everything has pros and cons, and it's up to people who actually run water systems to decide if it provides them sufficient benefit to actually execute on it. So that's all I'll say to that. So, no particular opinion. Everything is good and everything has some drawbacks.
Thanks for that. That pretty much wraps up the Q&A that we have here in the chat. If I will be sending all of these questions over to you, Branko, so that you can see who asked them if you wanted to do some follow-up conversations with folks. But thank you, everybody, for sending in your questions.
And there's a comment. Thanks for the thought-provoking presentation. I couldn't agree more, Branko. This is fantastic. We appreciate it. Branko has indicated a willingness to meet with interested parties to follow up and discuss, and we'd be happy to facilitate that. So please feel free to be in touch with me if you'd like to meet with Branko. And with that, again, Branko, thank you very much, and thank you all for attending.
Thank you. Bye.
All right, bye-bye.